Good day, everyone. Welcome to Elementary Theory of Numbers. Our topic is about Euclidean algorithm. I am your discussant for today, Miss Mary Heide Claire R. Hizole. The greatest common divisor of two positive integers can be found by listing all their positive divisors and choosing the largest one common to each. But this is not quite advisable for large numbers. A more efficient process involving repeated application of the division algorithm is given in the seventh book of the Elements, and is now referred to as the Euclidean Algorithm. It is named after the ancient Greek mathematician Euclid. The algorithm is as follows. Let A and B be two integers whose greatest common divisor is desired. Since GCD of absolute value of A and B is same as GCD of A and B, without the loss of generality, we can assume that B is less than or equal to A but greater than 0. By division algorithm, we have integer A is equal to quotient sub 1 times integer B plus remainder sub 1, where R sub 1 is greater than or equal to 0 but less than B. If R sub 1 is equal to 0, then B divides A and GCD of A and B is equal to B. Otherwise, if R sub 1 is not equal to 0, divide B by R sub 1 to obtain Q sub 2 and R sub 2, satisfying B is equal to Q sub 2 times R sub 1 plus R sub 2, where R sub 2 is greater than or equal to 0 but less than R sub 1. If R sub 2 is equal to 0, then we stop, and GCD of A and B is equal to R sub 1, otherwise proceed as before to obtain Q sub 3 and R sub 3, satisfying R sub 1 is equal to Q sub 3 times R sub 2 plus R sub 3, where R sub 3 is greater than or equal to 0 but less than R sub 2. This division process continues until some zero remainder appears, say at the n plus 1 stage, where R sub n minus 1 is divided by R sub n. A zero remainder occurs sooner or later because the decreasing sequence B is greater than R sub 1 and greater than R sub 2 and so on, and is greater than or equal to 0, cannot contain more than B integers. The result is the following system of equations. Integer A is equal to quotient sub 1 times B integer plus remainder sub 1, where R sub 1 is greater than or equal to 0 but less than B. Next is integer B is equal to Q sub 2 times R sub 1 plus R sub 2, where R sub 2 is greater than or equal to 0 but less than R sub 1. R sub 1 is equal to Q sub 3 times R sub 2 plus R sub 3, where R sub 3 is greater than or equal to 0 but less than R sub 2. We're going to continue until the remainder is 0. So let's say R sub n minus 2 is equal to Q sub n times R sub n minus 1 plus R sub n, where R sub n is greater than or equal to 0 but less than R sub n minus 1. Last is R sub n minus 1 is equal to Q sub n plus 1 times R sub n plus 0. It says that the last non-zero remainder is the GCD, or greatest common divisor. We argue that R sub n is the last non-zero remainder, which appears in this manner, is equal to GCD of A and B. Our proof is based on the lemma in this slide. Lemma 1, if integer A is equal to quotient times integer B, then GCD of A and B is same or equal to GCD of B and R. Proof: if GCD of A and B is equal to D, then D divides A and D divides B implies that D divides A minus Q times B, or D divides R. Thus, D is a common divisor of both B and D. If C divides B and C divides R, then C divides Q times B plus R, and hence C divides A. This makes C a common divisor of A and B, so that C is less than or equal to D. Therefore, GCD of B and R is equal to D. So lemma 1 implies that GCD of A and B is equal to GCD of B, and R sub 1 is equal to GCD of R sub 1 and R sub 2, and so on, and GCD of R sub n minus 1 and R sub n is equal to GCD of R sub n, and 0 is equal to R sub n as claimed. Let us see how the Euclidean algorithm works in a concrete case in the first example. We're going to determine the greatest common divisor of 12,378 and 3,054 and find x and y, where y is an element of any integers such that d is equal to 12,378x plus 3,054y. The first step is to 12,378 as a multiple of 3,054 plus the remainder. So we get 12,378 is equal to 4 times 3,054 plus remainder of 162. Well, of course, 162 is a unique remainder that is greater than or equal to 0 and less than 3,054. Now we're gonna do the same thing, but this time with integers 3054 and 162. We get the 3054 is equal to 18 times 162 plus remainder of 138. And then repeating the process, we have 162 is equal to 1 times 138 plus remainder of 24. By continuing, we get 138 is equal to 5 times 24 plus remainder 18, and then 24 is equal to 1 times 18 plus 6, and last is 18 is equal to 3 times 6 plus remainder of 0. Since the less than 0 remainder was 6, therefore GCD of 12,378 and 3,054 is 6. Next is to represent 6 as a linear combination of the integers 12,378 and 3,054. We start with the next to last of the equations and successively eliminate the remainder. First, we have 6 is equal to 24 minus 18 is equal to 24 minus the quantity of 138 minus 5 times 24 is equal to 6 times 24 minus 138 is equal to 6 times 162 minus 138 minus 138 is equal to 6 times 162 minus 7 times the quantity of 3054 minus 18 times 162 is equal to 132 times 162 minus 7 times 3054 is equal to 132 times 12,378 minus 4 times 3054 minus 7 times 3054. is equal to 132 times 12,378 plus the quantity of negative 535 times 3,054. Therefore, x is equal to 132 and y is equal to negative 535. Thus, we have 6 is equal to GCD of 12,378 and 3,054 is equal to 12,378x plus 3,054y, where x is equal to 132 and y is equal to negative 535. Note that this is not the only way to express the integer 6 as a linear combination of 12,378 and 3,054. Among other possibilities, we could add and subtract 3,054 and 12,378 to get 6 is equal to the quantity of 132 plus 3,054 times 12,378 plus the quantity of negative 535 minus 12,378 times 3,054 is equal to 3,186 times 12,378 plus negative 12,913 times 3,054. The number of steps in Euclidean algorithm usually can be reduced by selecting the remainder r sub k plus 1 such that the absolute value of r sub k plus 1 is less than r sub k divides 2, that is working with the least absolute remainders in the division. So it is more efficient to write 12,378 is equal to 4 times 3,054 plus 162 by continuing 3,054 is equal to 19 times 162 minus 24, and then 162 is equal to 7 times 24 minus 6, and 24 is equal to negative 4 times negative 6 plus 0. As evidenced by this set of equations, this scheme is to produce the negative of the value of the greatest common divisor of the two integers, the last non-zero remainder being is negative 6, rather than the greatest common divisor itself. An important consequences of the Euclidean algorithm is the theorem 11. If k is greater than 0, the GCD of k times A and k times B is equal to or same as k times GCD of A and B. Proof by Euclidean algorithm for A times k and B times k, we have A times k is equal to q sub 1 times B times k plus r sub 1 times k, where r sub 1 times k is greater than 0 but less than b times k. B times k is equal to q sub 2 times r sub 1 times k plus r sub 2 times k, where r sub 2 times k is greater than 0 but less than r sub 1 times k. R sub 1 times k is equal to q sub 3 times r sub 2 times k plus r sub 3 plus k, where r sub 3 times k is greater than 0 but less than r sub 2 times k, and so on, and r sub n minus 2 times k is equal to q sub n times the quantity of r sub n minus 1 times k plus r sub n times k, where r sub n times k is greater than 0 but less than r sub n minus 1 times k. Last is r sub n minus 1 times k is equal to q sub n plus 1 times the quantity of r sub n times k plus 0. Therefore, the GCD of k times A and k times B is equal to R sub n times k is equal to k times GCD of A and B. Thank you and have a great day today.